Oh, hello. Welcome back to more AP Stats review packet. Uh, this is my second round at this problem, but then my computer lost its mind, so it's our first time together here. So we play a game at the fair. It costs $2 to play. It's going to come in later. You have a 70% chance of winning nothing, a 20% chance of winning $2, an 8% chance of winning $5, and a 2% chance of winning $20. How much do you expect to win? So every time you see this word, expect, think expected value and think mean. Right? Expected value and mean. Get used to using those interchangeably. So I'm going to make a table like the one down here for this problem. I'm going to use Y instead of X because it's X down there. And I'm just going to organize the amounts just like they have in the table below. So 70% chance of winning nothing, that's $0. And that's the highest percent chance. 20% chance, so 0.2, of winning $2. An 8% chance of winning $5. And a 2% chance of winning $20. Okay, cool. So, two ways to do our expected value here. The first way would be to say, okay, 0 times 0.7 plus 2 times 0.2 plus 5 times 0.08 plus 20 times 0.02. And so this is just the value, the winning, times the probability of that. And when we add those all up, that's our expected winnings. Now, the one thing you have to take into account, though, is 2 times 0.2 plus 20. What we have to take into account, though, is you have to pay $2 to play this game to begin with. So the wording here is a little bit ambiguous. You could say you expect to win $1.20. Or if you're thinking about your net winnings, we'd have to subtract $2. And so we'd actually get that we're expecting to lose 80 cents. Okay, we're going to go with this because I think you should factor in the cost to play. Now, another way to look at this, another way to calculate both this 80 cents and what we're going to need later, which is our standard deviation, is to use our calculator and use our lists with this information. So you're going to go to Stat, Edit, and then in List 1, you're going to put your values. So I'm going to say 0, 2, 5, and 20. If you wanted to do the minus $2 at this point, that's also fine. And then the probabilities are 0.7, 0.2, 0.08, and 0.02. Okay, so once we have this, again, that's in list 1. List 1, and this is in list 2. This is going to be our X list. This is going to be our frequency list. Remember, you can calculate standard deviation with probabilities as the frequency. So we're going to go to one variable statistics. In list 1, we have our values. In our frequency list, we're going to put the list with our probabilities. I've used 1 and 2. It doesn't matter which list you use as long as you remember which is your values and which is your probabilities. Okay. So our expected value, our mean, was $1.20 again. So then we'd subtract the 80 cents, or excuse me, we'd subtract the $2 and end up with losing 80 cents. And so this is our mean. And our standard deviation, is 3.059. We don't have to worry about subtracting the $2 from this because remember, standard deviation is a measure of spread. So it's about how far apart the numbers are from each other on average, not about the actual values in a sense, right? The subtracting 2 from each value or overall is not going to change how far apart these are spread based on their probabilities. Okay, so again, expected value is our mean. Cool. Now, imagine you play the game next to the one in question 13 as well. So we're at the fair, having a good time. This one costs $1 to play. So we're going to subtract $1 at the end. And the winnings and probabilities are in this table below. So what are the mean and standard deviation of the winnings for this game? So again, I'm going to put this in list 1 and my probabilities in list 2. And so for my X values, I have 0, $2.50, or $100. Lucky that person. Probability of winning nothing is 0.85. Probability of winning 250 is 14.5%. And the probability of winning $100 is 0.005. So 0.5%. Low chance, high reward. So once again, once I have those in my list, I'm going to go to Stat, Calc, and then one variable statistics. And list 1 is our list, and our frequency list is list 2. And then when I hit calculate, I get a mean of 0.8625, so about 86 cents-ish, and a standard deviation of 7.083. And it makes sense that our standard deviation is higher for this set because this maximum winnings only went up to $20. This goes all the way up to $100. So even though it's a little bit, we've got something pulling on that standard deviation quite a bit. Now, we have one more step though, because this game costs $1 to play. So we need to subtract 1 from this. And when we do that, we get 0.8625 minus 1. We get negative 13.75 cents, or negative $0.1375. Okay, so there's the mean and standard deviation. Next up, what are the mean, mu, and standard deviation sigma for your total winnings if you play both games? So basically, we're looking for the mean of X and Y and the standard deviation of X and Y. So for the means, we can just add them. We've got negative 0.1375 plus negative 80 cents, right? That was our mean from the first one. For our standard deviations, though, when we're combining, we always want to use that Pythagorean theorem of statistics. So 1 standard deviation squared plus the other standard deviation squared, 3.059. And then rather than having this be squared and be the variance, let's just pop the square root over here. So it's still just a squared plus b squared equals c squared. We're just moving that c squared, taking square root of both sides, doing that. Okay, so when we do that, we get our mean of negative $0.9375. And our standard deviation, and 7.083 squared plus 3.059 squared. And we're dealing with money, so we'll only go to 2 decimal places. I like to go to at least 4 or 5, or I guess 3 in this case, while I'm calculating, just so that I'm not rounding too aggressively and too early. So when I do that, I get a standard deviation of 7.7 Okay. So what's the probability that you win more than $0 combined by playing each game once? So the probability that you win more than $0 combined by playing each game once. So we have game 1 and game 2. This is our X game and this is our Y game. And in game 1, we have the chance of winning 0, 2, 5, or 20. So 0. But I'm going to subtract 2 from that. So -2, 0, because 2 minus 2 is 0. 5, but minus 2 is 3. Or 20, 18. And again, our probabilities here, 0.7, 0.2, 0.08, 0.02. So 0.7, 0.2, 0.08, 0.02. And then for game 2, we have 3 possibilities. We can, if winning 0, but you spent $1, so that's going to be -1. You could win 250, but you spent $1, so that's going to be net 150. Or you could win $100, but you spent 1, so that's 99. And those probabilities, again, this is 0.005, and this is 0.14. What was that? 0.145, and this was 0.85. Okay. So we're going to find all the places that add up to more than $0 combined. Oops. And then we're going to multiply those probabilities. So let's see. -2 plus -1 is not more than 0. 0 plus -1 is not more than 0. 3 plus -1 is 2. So that'll suffice. And 18 plus -1 is 17. That'll work. Then 18 plus anything else is going to satisfy. 3 plus anything else is going to satisfy. So I'm going to fill these in. And then here we've got 0 plus 1.5. That's going to be more than 0. -2 plus 1.5 is not. But then these guys plus 99 will definitely work. So now this is kind of like a big old area model, just like Math 1. We're just going to multiply and find the insides. So 0.85 times 0.08, 0.85 times 0.08 is going to be 0.068. Then we keep going. So now it's the probabilities times each other. So 0.85 times 0.02 is 0.017. We keep going. 0.145 times 0.2, 0.029, 0.145 times 0.08 is 0.0116, and 0.145 times 0.02 is 0.0029. Last but not least, 0.7 times 0.005, 0.0035. I could have done that one. 0.005 times 0.2, 0.001, 0.08 times 0.005, and it's 0.0004, and 0.02 times 0.005 is 0.1234. Great, now we just add all these up. So plus that, plus 0.001, plus 0.0035, plus 0.0029, plus 0.0116, plus 0.029, plus 0.017, plus 0.068. So this is about a 0.1335 if I added those all up correctly. So that's our chance of winning more than 0. So we have 0 and then that. If you used a normal distribution, we don't actually know upon further reflection. We're not actually told that this is normal, and in fact, it probably isn't normal. But if you did this with a normal curve and put your mean and you found, okay, here's where 0 is and what's the probability of being above that, what you would get is about 45%. So apologies if you went down that normal path. This, you probably want to set up this way. In many situations outside of playing games like this, you're going to be dealing with a normal distribution. Okay, onward. Number 9, something completely different. A least squares regression line for predicting NBA player height in inches based on weight. So predicting height in inches based on weight. So this is the explanatory, and this is the response. Just to think about that. Here's our equation. You could think about this as y hat and x. Sometimes you'll see the word, sometimes you'll see the variables. If you use variables, make sure you define them. So first it says identify and interpret the slope in context. Okay. Slope is always the coefficient on the explanatory variable. So here's our coefficient on the explanatory variable. So that is 0.0573. And what that means in context is, on average, for each additional pound of weight, the NBA player's height is predicted to increase, because it's positive, by 0.0573 inches. And yeah, you need to be that specific. Okay, so that's for part A. So again, the slope is always the coefficient on the explanatory variable. Now, for identifying the y-intercept then, it's the other number. So for B, the y-intercept in context, 66.74 inches for a weight of 0 pounds. That doesn't make sense in context. So, not reasonable in context. So again, every line, except for vertical lines off of the y-axis, every line has a y-intercept, every straight line. A least squares regression line in our context is going to be straight, so it's got to cross the y-axis somewhere. We're not really expecting people's weight to be 0. Most people, professional basketball players' weights are probably much higher than that. But if the trend continued, eventually at a weight of 0, the height would be predicted to be 66.74. This is a good example of why extrapolation, or trying to use a model for values, input values way outside the range you use to create the model, doesn't always work. So that's, again, extrapolation. All right, C. Kevin Durant is 6'10" and weighs 240 pounds. What is Kevin Durant's residual? And what does the sign plus or minus mean in context? Okay, so first let's change 6'10" inches into just inches, because this is height in inches. 6 feet is 72 inches. So this is going to be 10 more than that. So 82 inches. So the predicted height based on a weight of 240 pounds is our regression equation, but where it said weight, we're going to pop in 240. Okay. So when we do that, 66.74 plus 0.0573 times 240, we get that the predicted height is 80.492. Residual is always y minus y hat, or actual minus predicted. So the residual here is going to be 82, the actual, minus the predicted 80.492. And when we do that, we get 1.508. So in context, the positiveness of this, the positive sign on it, means that Kevin Durant is 1.5 inches taller, right? Because it was positive, than this model predicts. If it was negative, that would mean he's shorter than the model predicts based on his height. Or excuse me, based on his speed. Okay, residuals. Now for something completely different, averages. So a student has taken 3 exams so far for a class and scored an average of 80. There are 5 more tests this semester. What must the student's average be on those 5 tests in order for her overall average to be a 75? Every time you're thinking about average, think sum over the number equals the average. So the sum in this case is all the exam scores added up. So we know that 3 exams had an average of 80. So in order for them to average 80, their sum had to be 3 times 80. Another way to think about that is the simplest way to have an average of 80 on 3 tests is to get exactly 80 each time. There are 5 more tests this semester. What must the student's average be on those 5 tests? So we don't actually know what this average needs to be yet. That's what we're solving for. So in math, we use a variable to represent what we don't know. Overall, there are going to be 3 plus 5 tests. So that's 8 tests total. And we want the overall average to be 75. Now it's just algebra. We're going to multiply both sides by 8, and these will cancel out. We get 75 times 8. And 3 times 80 is 240, plus 5x is equal to 600. We're going to subtract 240 from both sides. And even if you think you don't need to, write it out. Minus 240 minus 240. So 5x equals, 360. And then last but not least, we want to isolate x. We want to isolate x by dividing both sides by 5. And we get x equals 72. So the average on those 5 tests needs to be 72 in order for the overall average to be a 75. Now, just kind of gut checking this. So far, the student has an average of 80. We're going to take more tests and end up with an average of 75. So the additional test scores can be lower than 80 because they're going to pull the average down. And they're actually going to be lower than 75 because in order to pull some 80s down to a 75, we need to be lower than 75 to have that effect. Okay, averages on averages. Next up, more residuals. So for this linear regression equation, find the residual for this point. Okay, So this is our X, this is our Y. We need to find Y hat, right? Residual is Y minus Y hat. So we have Y, that's a 4. We need to find Y hat. So Y hat is going to equal 3.5 minus 0.017 times 3. And when we do this, 0.017 times 3, we get 3.449. So this is our Y hat from plugging in our explanatory variable, or our X. This is what the equation, the model, predicts the outcome to be. This is what it actually was. So we'll do actual minus predicted and get 0.551. There's no context for this problem, so we can't really take it any further. This is more a practice of calculating the residual. Not likely to see a question that's just this, but never know. Okay. Number 12. Two variables that are actually not related to each other, that's key, may nonetheless have a very high correlation because they both result from some other, possibly hidden factor. This is an example of a lurking variable. So again, I talked to a few of you about this today. Lurking variables are when X and Y appear to have a relationship, but actually they don't, and it's something else driving them. Confounding, which is the one that people most often get confused with here, is when X and Y do have a relationship. So this is what makes it not confounding. Confounding is when X and Y do have a relationship, but it's hard to tell the extent of that because of some other contributing factor. Okay. Cool. 13. You want to take a simple random sample of 100 of the 700 students who attend PGHS. You label the students 1 to 700 in alphabetical order. In the table of random digits, you read the entries, and then here's some random digits. What are the labels of the first 3 students in your sample? Okay, so because our labels are 3 digits, we have to block off by 3 digits. And you don't just shift, you block off in 3s. I'm just doing this whole thing. Don't feel like you need to do that, but it could be helpful, especially if you're only looking for 3. Next up, our highest number is 700. So anything above 700s, like this 716, that can be crossed out. This 918, that can be crossed out. Okay, so those are not part of our population, so we can't pick 716 because we're only labeled to 700. So the labels of our first 3 students would then be 655, 678. Here's 678 again. You're not going to sample the same student twice. So this is another one that gets crossed out, not because it's an invalid number for the range part of it, but because we've already got a 678. We've already got that student. And so then the next one on our list is 548, and there are our first 3 students. Okay, got a lot of later in the alphabet folk. All right, getting there. PH admin team wants feedback on the new bell schedule. One day, my friends. Name the sampling strategy for each of the following situations. Okay, so sampling strategy. So these are for observational, sampling. It's not experimental stripes. So first, there are 4 years of students, freshmen, sophomores, juniors, and seniors. You randomly select 50 students from each year. So because you're splitting your population into groups that might have some shared characteristics like freshmen, sophomores, juniors, seniors, and then selecting the same amount or proportional amount from each of those groups, this is a stratified random sample. And the strata are the class years. Good. Randomly select 10 classes and survey every student in each of those classes. This is a cluster sample. And in this case, the classes are our clusters. So again, the difference here is stratified is some of each group, and a cluster sample is all from set groups, in this case, the classes. Okay. C is randomly select 200 student ID numbers and survey the students. This is a simple random sample. So when you see SRS, that always stands for simple random sample, even though a lot of our sampling types could be abbreviated SRS, which is very confusing. I don't like it. And then D, randomly select a number between 1 and 65 using a list of student ID numbers. Start at the randomly selected number and then survey every 65th student from the list after that. This is a systematic random sample. So it's systematic because you're randomly choosing a starting point, but then based on how many you want, how many responses you want, you're sort of surveying one every X number of people. Okay. Getting there. 15, costs for standard haircut services at a local salon follow a normal model with a mean of 100 and a standard deviation of $18. Draw and clearly label a model for the situation. So when in doubt, or even when not in doubt, draw it out. Our mean is in the middle. Our mean plus 1 standard deviation is at the first inflection point. Mean plus 2 standard deviations, and then mean plus 3 standard deviations. And we go the other way. Mean minus 1 standard deviation, mean minus 2 standard deviations, and mean minus 3 standard deviations. Now we put our numbers in. Oh, goodness. So there's our 100. And it's a standard deviation of 18. So this would be 118, 136, and 154. Am I adding that correctly? I think so. That's the hardest part of math, honestly. Okay. And then we go backwards. So this is going to be 82, and then 64, and then 46, right? 100 minus 54. Yeah. Okay, cool. So draw and clearly label a model for this situation. We could put $ signs on all of these because the context is that it's money. Okay. So what is the Z-score for a service that costs $85? So first, just gut check. 85 is somewhere here between 82 and 100. It's below average. Our Z-score should be negative. Z-score tells you how many standard deviations you are away from average, and the sign tells you whether you're above or below. So Z is equal to actual minus mean over the standard deviation. So in this case, our Z would be 85 minus 100 all over our standard deviation. When you do that, you get negative 15 over 18, which is about equal to negative 0.83. Repeating. Great, there's a Z-score. Approximately what percent of services cost less than $85? We can do this with our numbers, and we're looking for a percent. Whoops. We're looking for a percent, so that's going to be our normal CDF because we're in normal world here. Okay, so normal CDF, and I don't know why I wrote that so small. I can just... And what we're going to put in here, since it's cost less than $85, we're going to use a placeholder for negative infinity. put 85 as our upper bound. So this is lower, this is upper. Our mean is 100 and our standard deviation is 18. When we pop that in, 85, 100, and 18. When we pop that in, we get about 20%. If services cost less than $85, which makes sense again. This is not nothing, right? This is a decent amount of that normal distribution. 20% makes sense there. Same thing, different direction. What's the z-score for services that cost $125? So again, z is equal to actual minus mean over standard deviation. So we've got actual minus mean over standard deviation, which is 25 over 18. And so our z-score is about equal to 1.39. And it's positive because 125 is up here above average. Okay. What percent of services cost more than $125? Again, we're going to have our normal CDF. Oh, I didn't label these. Mean, standard deviation. And this time, we want what's more than 125. So let's set that as the bottom. Let's set essentially positive infinity as the upper bound. And then the mean and standard deviation are exactly the same. And always label upper, mean, and standard deviation. When we do that, 125, 1 times 10 to the 99th, we get about 8%. Which again, makes sense. This is beyond 1 standard deviation above the mean. There's not very much left up there. So 8% is not unreasonable. Okay. Onward and upward. Oh, a histogram? How rude of me. Okay. Table shows the frequencies for the 9 different values that occur in a 31 item data set. Create a histogram. Now, there aren't units here, but I'm still going to label this as much as possible. So my histogram, I'm going to use boxes of bin width 2. So these are going to be in one box. 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 And then this will sort of be its own little box. Okay. And just for good measure, I'm just going to break that there so it's not exactly at 0, 0. And over here we have the frequency. And over here we have the values. And we're going to go from, I'm going to say this is 33. And like this is 35. This is 37. This is 39. This is 41. And this is 43. Again, you could do this with bin widths of 2, 1. I wouldn't necessarily go all the way to 3 in this case because you're going to start to lose some of your picture. But the number of values that are either 33 or 34 would be 4 plus 7, which is 11. So it's not going to get much higher than that. So I'm going to say here is 10. Here's 20, 15, and 5. Again, if you label it, it's so. No one expects you to be a robot. You just have to label it so it's clear that you know what you're doing. Okay, so we've gotten those. Now we've got 6 and 5 also makes 11. Yeah, that's going to be our highest is 11. Okay, taking care of those. 37 and 38, 3 and 2 make 5. So that's going to be here. 39 and 40, which fit into this bin, because this again is 39 up to, but not including 41. So that's going to be 3, a little more than half of 5. And then 41 to 43, so including 41, but not 43, there's only one of those. Okay. there's our histogram. Now, to create the 5-number summary, I'm going to pop this into my lists. Again, we've been doing that a lot. I think it's something that y'all are getting good at, so let's use it. So the values are going to be list 1, 33, 34, 35, etc. Make sure you don't skip one. You'll get a dimension error. And then for the frequencies, 4, 7, 6, 5, 3, 2, 2, 1, 1. Now we go to stat and calc and one variable stats. So again, this was list 1, this was list 2, stat, calc, one variable. And the list is L1, the frequency list is L2, and then you calculate. So the 5-number summary is the minimum, Q1, the median, or Q2, Q3, and the max. And if you scroll down a little bit from your one variable stats, you'll actually get all these things. So the minimum is 33, Q1 is 34, the median is 35, Q3 is 37, and the max is 41. You could figure a lot of that out from here, but the quartiles start to get a little annoying, so letting your calculator do it is great. Now, when you're drawing a box plot, you need to have a scale. If there's units, label it. I know it goes up to 41, so I'm going to maybe say that this is like 45. I'm going to say this is like 30. And then there's 15, so maybe this is 35 and 40. That seems about right. So our minimum is at 33, which is a little more than halfway here. So I'm going to draw a line there. Q1 is at 34. I'm going to draw a line approximately where 34 would be. 35 is our median. Q3 is 37, so it's a little bit further out here. And then our max is 41, which will be out here. Make my box, makes my whiskers, and I'm done. This is relatively concentrated data, so I'm not going to check for outliers. If you wanted to do a box plot with outliers, then you could calculate those, draw the boundary at the last value within, and then little stars or dots for the outliers. Median value of the data set is, again, from here, 35. And your one variable stats will actually give you the mean as well, which in this case is 35.68. So pretty close. And that makes sense. Most of the data is concentrated around here. There's not a ton over here pulling it, up. So kind of makes sense. All right, last but not least. What? I thought there were only 17 questions. Okay, we've got this. Certain variety of table groups has fruit diameters that are distributed normally with a mean of 13 millimeters and a standard deviation of 2. Approximately what proportion, see proportion, percent, if it's normal, think normal CDF, have diameters between 12 and 16. They're literally just telling us everything. We just need to know to plug it in. You could go through a big hassle with z-scores here, but don't. Between 12 and 16, so there are our lower and our upper bounds. Our mean is 13. And our standard deviation is 2. When we pop that in, 12, 16, 13, and 2, we get about 62%. Which makes sense. We're surrounding the mean, so we're right in the bulk of that data. Okay. That is it. 18, multiple choice. A florist wanted to investigate whether a new powder added to the water of cut flowers helps to keep the flowers fresh longer than just water alone. For a shipment of roses that was delivered to the store, the florist flipped a coin before placing each rose in its own individual container with water. If the coin landed heads up, the rose was placed in water with new powder. Otherwise, the rose was placed in water alone. Which of the following is the best description of the method used by the florist? Okay. So, a census because all roses are assigned to a container. This is not really sampling. This is more of an experiment. So, census doesn't apply here. An experiment with a completely randomized design. That seems pretty good. She just flipped a coin. Each rose, the treatment was determined by the coin flip. So we'll leave it on the table. An experiment with a block design with blocking by type of water. Well, not really, because that's what we're testing. You don't block on what you're testing. You block on what you're not testing. So like if you wanted to block on rose color or rose origin, that would be reasonable. An experiment with a matched pairs design. No. Completely randomized makes more sense because it wasn't like she had a pair and one was randomly assigned to the treatment and one was randomly assigned to the control. And an observational study, no, because a treatment is being applied. She's randomly assigning treatment. It has to be B. Okay. 19. For the purpose of determining the value of its year-end inventory, a clothing store creates a list at the end of the year of every item currently in stock. I'm going to underline that, every item currently in stock, along with each item's wholesale price. Which of the following is the best description of the end of the year activity? An experiment because the items and treatments and wholesale prices are responses? No, that doesn't make sense. An experiment because the store does not know the total? No, because no treatment's being applied. We are creating a list. So if you're just collecting data, you're not applying treatments. This has to be some sort of observational situation. See, a sample survey because the store wants to estimate the value of all items for the entire year. No, we're not estimating. Sample survey because the items currently in the store at the end of the year are a random sample of all items in the store for the entire year. But that's not what we're trying to do. They want to determine the value of its year-end inventory. A census because the wholesale prices of all items are listed. The key here is all. A census is when you're collecting data from every bit of the population. We're surveying every item in this store, recording how much it costs, and then probably totaling that up, determining the value of its end of year inventory. Okay. 20. Oh, we got this. If random variable y has a geometric distribution and its mean is 25, what is the standard deviation? Okay. On your formula sheet, you'll see on the front, one of the distribution types is geometric, and then next to the setup is the mean. So the mean of a geometric distribution is 1 over p. And also on that formula sheet, the standard deviation is, oh, I should have pulled up the formula sheet already, but hold, please. Bloop, bloop, bloop. And classwork. And just so you know, I have the formula sheet in the classwork view of Google Classroom. Okay, so the mean of a geometric distribution is the square root of 1 minus p probability over p. So really what we need to know here is probability. So we know the mean is 25. So I'm going to say 25 equals 1 over p. Then I just algebraically isolate p. So multiply both sides by p. And we get 25p equals 1. Divide both sides by 25. And we get p equals 1/25. Cool. If you know the trick that these just switch, that's fine. It always works to solve it algebraically. So then to find our standard deviation, we're just going to plug that in. So the square root of 1 minus 1/25 all over 1/25, when we do that, 1 divided by 25 is 0.04. 1 minus that is 0.96. Square root of 0.96 over 0.04. So I've just popped this all in my calculator and I get 24.49. Okay. So mean, standard deviation, these are pretty close to each other just by nature of how this works out. That's okay. Sometimes that happens. Sometimes they're farther apart. Last but not least, extrapolation. Extrapolation is when you use a regression model to try to predict a response value for an explanatory value not contained in the range of explanatory values used to create the model. Right? So if you're like, a little bit away, your data for the model ends at 20 and you have something that's 21, and that's not like super far away relative to whatever you're looking at. Like, yeah, okay, that is extrapolation, but like maybe that's okay. But if you're in a situation where the values you're using to build the model are between like 10 and 20, and then you want to use that model to predict something with an input value of like 20,000, we have no guarantee that what's happening from 10 to 20 is going to continue all the way up to 20,000, right? So that's way far out there. All right, we did it. Yeah, we did it. And I was just checking the time here. This is really important. A lot of the questions on your test come from those progress checks. So that's your little Easter egg if you made it this far. I hope that was helpful, and I will see you in class on Thursday. Goodbye.